Okay, here I have an air conditioning system. Refrigerant 22 is the working fluid going through everything, and I've got properties shown on the system right here. Okay, and what it says is the evaporator removes energy by heat transfer from the room air at 600 BTUs per minute. So again, that's the energy moving from the air into my system. So this is actually Q in to my system. Again, it's pulling heat from the air into my system. So that's why it's Q into the system, even though I'm kind of pulling heat out of the room itself. Okay? So, it's a few things I want to find. I want to find, actually, there's a heat transfer at the compressor, and then I want to find the coefficient of performance. But the first thing I need to do is I need to go through and I need to set all of my states, which is finding H values for 1, 2, 3, and 4 for the refrigerant 22. So I'm going to look up H1, H2, H3, and H4. So H1, this is R22, is 120 psi, 62 degrees Fahrenheit. Okay, so I start at 120 psi, 62, 120. So 120 psi. Oh, that's water. Excuse me. Here's 120 psi for refrigerant 22. This is table A9. Okay, and then what was my temperature? 62. So if you notice, I'm pretty much at saturation here, 61.92. So my H value is approximately 109.88. I'm going to go ahead and round 61.92 to 62 degrees. So I'm at saturation. My H value is 109.88. State 2 is 225 psi. Oh, it already gave me H2, so I won't worry about that one. State 3 is 100 Fahrenheit at 225 psi. So I go to 225 psi, and I'm at 100 degrees. At 100 degrees, okay, that is me actually below saturation. Okay, at 225. So I approximate that as a saturated liquid at, what was it, 100 degrees. So I go to 100 degrees for the saturated liquid table. Okay, and I'm, again, yes, above that pressure. So my enthalpy would be approximated as a saturated liquid, which would be 39.41. Okay, because again, I just recognize that, hey, I'm actually a saturated liquid. Or I'm sorry, I'm a compressed liquid. I don't have those tables, so I approximate it as saturated at that temperature. Okay. Now H4 is on the other side of an expansion valve, a throttling valve, so the H is constant from H3 to H4. So let me go ahead and go through here. Again, H2 was given to me. That's 130. H1 I looked up. That was pretty much saturation, so I call that 109.88, and these are all BTUs per pound. And then H3 and H4 are both 39.41, and again, they're equal. And state 3 I approximate as a saturated liquid at 100 degrees because, again, I'm below that vapor dome, but I don't have a table for it. So I've got all of my H values. Okay. The next step is to find my mass flow. And the way that I'm going to find my mass flow is knowing this heat transfer, this Q in, right? Because that Q in, by definition, is my mass flow that I'm looking for times the change in H, right? Because there's no work being done. This is a heat exchanger. There's no kinetic, there's no potential energy here. Okay? The only thing I have is I know my H values, and I know that it's 600 BTUs per minute. So that mass flow then becomes, well, just plugging in the values for everything. Let me go ahead and put, that equals 600, right? And then plugging in H1, H4, I actually get my mass flow to be 8.5 pounds per minute. Okay, so I set my states, then I find my mass flow, knowing Q in at the evaporator and knowing H on either side, I can then calculate out my mass flow. Now that I have my mass flow, I can go ahead and try to figure out what's going on with the compressor, because I know I have an input power. I also could potentially have heat transfer, which is what I'm looking for. So my first law equation across the compressor is my mass flow times the change in enthalpy. That'd be H2 minus H1, and that equals my heat transfer across the compressor minus the work across the compressor, which I know to be 200 BTUs per minute. This is 200, right? I'm looking for Q. I now know my mass flow. I know H2, I know H1. The only thing I don't know in this equation is the Q, the heat transfer. So my heat transfer then becomes negative 29 BTUs per minute. Negative means I'm losing heat. So this is heat lost during the compressor process. Okay, so that's the first part. The next thing is, hey, what's the coefficient of performance? Remember, coefficient of performance is essentially output over input. This is an air conditioning system. What I'm trying to do is take heat from my room, trying to cool that down. So Q in is my objective. That's my output. My input is the power. So that's going to be, the work put in. I have both of these. I don't really need any of my H values or anything because I know Q in is 600. I know the work is 200. Therefore, my coefficient of performance is 3. So again, set your states, find your enthalpies, figure out your mass flow. Here I found it, knowing my enthalpies and my heat transfer across the evaporator. Once I have those things, then calculate what it's trying to find. So I found the heat here, knowing the work and the enthalpies on each side. And then I found my coefficient of performance just based on what I had already been given.